virtual reality. But now it feels like even as 5G deployment is finally hitting its stride globally, the entire wireless ecosystem is already shifting focus.
Yeah, pouring massive resources into 6G.
It just seems almost counterintuitive, doesn't it? I mean, why, when we finally have 20 gigabits per second in our pockets, is the industry ready to just tear up the playbook?
It is a phenomenal rate of change. But what's really essential to grasp here is that 6G is not just an upgrade. It's a necessary reset.
A reset.
Yeah.
Yeah.
Our primary source for this, the roadmap laid out in 6G Unleashed, makes a really compelling case that 5G, despite all its genuine triumphs, it just runs into these fundamental sort of non-negotiable walls.
Physical walls.
Physical and architectural walls, yeah. They just block the next stage of global technological maturity.
So that really sets our mission for this deep dive then. We need to move beyond just the superficial story of speed and bandwidth.
Right.
The goal, for you listening, is to understand not just the why 5G is insufficient, but the how. The how of the 6G architectural revolution.
Exactly.
We're going to explore the blueprint that, fundamentally turns connectivity into pervasive intelligence and overcomes these invisible limits that 5G just couldn't cross.
Limits around energy, latency, and coverage. Big ones.
Big ones.
And if we zoom out for a second and just look at the trajectory of mobile communication, the shift it's profound.
How so?
Well, the 2G through 4G generations were, they were primarily dedicated to optimizing connectivity, just getting reliable voice, data, and video to users.
Right, making the phone work better.
Pretty much. 5G was that pivotal move toward enabling intelligence. It was driven by the cloudification of the core network and the capacity for massive IoT.
Okay, so if 5G enabled intelligence, where is 6G taking us next, based on the thinking you've analyzed?
It's taking us to the era of full human-machine integration and pervasive digital sensing.
Pervasive sensing, what does that even mean?
It means the networks of the future won't just transmit data. They'll autonomously sense the world around them, predict what's going to happen, and then optimize for it.
Wow.
Our source describes this as the transition from past connectivity networks through present intelligence systems, that's 5G, to future integration networks, that's 6G. It's really about creating a true planetary scale sensory fabric.
Before we, get into dissecting all the shortcomings, we have to recognize that 5G was a success story. It really was.
Oh, absolutely. It was the necessary evolutionary step.
And the source material confirms it delivered on, nearly 80% of its original specifications.
That's right, which is a massive technological achievement in itself.
It really is. It sort of provided the foundation we needed to even understand what the next set of problems were.
Absolutely. And those achievements, they fall pretty neatly into the three foundational use cases we're always hearing about. The first, and I think most visible one, is enhanced mobile broadband, the EMBB.
Right, this is the one everyone talks about, the speed and the capacity.
Precisely. We saw early urban trials, particularly in dense places like Seoul and certain U.S. cities, demonstrating peak downlink speeds that were consistently hitting 10 to 20 gigabits per second.
Which is just fiber-like speed.
It is. And that kind of throughput unlocked genuine high-capacity applications. I mean, think about large events like the Tokyo Olympics. 5G enabled multi-angle immersive viewing and high-res AR, streaming directly to thousands of users all at once.
Out in the same place.
Right, in very close proximity. That capability, handling those massive data flows instantaneously, that was fully validated.
Okay, and the second pillar was ultra-reliable low-latency communications, URLLC. This is where 5G really started to move out of the consumer space and into the industrial world.
This is the critical piece. This is what paved the way for Industry 4.0. We saw genuine success stories all over the world.
For example?
Well, in highly automated manufacturing centers, especially in Germany's auto sector and Japan's precision robotics, real-world deployments achieved sub-5 millisecond end-to-end latency.
Which 5 milliseconds might not sound like a lot to most people.
It might not, but for precision manufacturing control, where robotic arms need these immediate feedback loops for synchronization and safety, that level of responsiveness validated the core promise. The promise of using wireless for mission-critical industrial systems.
And then finally, you have the sheer scale of connection needed for a world just saturated with sensors. Massive machine-type communications, or MMTC.
Right. 5G had to prove it could handle orders of magnitude more devices than 4G ever could.
And did it?
It did. Controlled tests show the ability to scale connectivity right to that benchmark of 1 million devices per square kilometer.
1 million devices.
1 million. And that capability underpins the whole modern vision of the smart city, right? It enables widespread deployment of low-power sensors for infrastructure, utilities, logistics, all without overloading the network. So yes, 5G did deliver.
But, and here's the big but, the very act of deploying 5G at scale is what exposed its fundamental flaws. We hit these invisible walls that limited both the reach and the efficiency of the tech.
Exactly.
Let's start with the hard physics constraint, the one that defines 5G's failure to give us that ubiquitous coverage. Let's talk about the coverage gap.
This is a massive economic and physical hurdle. 5G relied heavily on high-frequency spectrum, specifically millimeter wave signals, typically above 24 gigahertz, to get those blazing fast speeds.
But there's a trade-off.
A severe one. It's severe physical attenuation. To put it simply, these signals are they're terrible at penetrating physical objects.
So they travel very fast, but they don't go through things.
Exactly. They get easily blocked by walls, concrete, glowy glass you find in modern office buildings, even dense vegetation, rain fade.
Or just a person.
A human body standing between your phone and the antenna can cause the signal to drop significantly.
Okay, that explains the frustrating consumer experience then. You get great speeds if you're line of sight with the antenna outside.
Right.
And then the speed just falls off a cliff the moment you step indoors or even turn a corner.
And the operational impact of that for carriers is it's crippling. To get reliable coverage in dense urban areas, operators are forced into this incredibly expensive and massive densification strategy.
Meaning more towers.
More and smaller towers. They have to deploy these small cells, which are small, low-power antennas, basically every 200 to 300 meters.
So it clutters up the city.
It clutters the infrastructure, and it dramatically increases capital expenditure, the CapEx. And because those millimeter signals don't travel far, they completely fail to deliver uniform coverage in rural or remote areas, leaving huge parts of the globe untouched. 5G fundamentally failed the universal coverage test because of propagation physics.
All right, second limitation. This one is arguably the most frustrating for developers who are trying to build these advanced automation systems. I'm talking about the latency floor. We were promised 1 millisecond.
We were.
But the real-world performance is more like 3 to 10 milliseconds. Why couldn't the 5G architecture break that final barrier?
This is a systemic architectural problem. The radio link alone can't fix it.
It's deeper than that.
Much deeper. The source material shows that the latency floor isn't dominated by the time the radio wave takes to travel. It's dominated by delays in the transport network, the fiber backhaul, and, crucially, the processing time inside the core network.
The thinking time.
The thinking time, exactly.
Yeah.
Even with an optimized 5G standalone architecture, the computation required to make a critical decision still needs a round trip to a core processing location.
So even if the signal gets there in a flash, the decision takes too long because the brain is still too far away.
Precisely. We need microsecond responsiveness, that's under 1,000 microseconds, for things like real-time haptic feedback in remote surgery, or for enabling cooperative perception between autonomous cars. 5G's inherent design, where computation still lives somewhat centrally, just can't shrink those non-radio delays enough.
And the third issue, and this might be the greatest threat to 5G's long-term viability, the energy crisis. We hear about the benefits, but the operational cost of running it is becoming, well, unsustainable.
This is the operational expenditure, the OpEx nightmare. The capacity gains in 5G rely heavily on massive MIMO radios.
Multiple input, multiple output.
Right. They use dozens, sometimes hundreds of antennas to manage multiple data streams at once. And while they're brilliant for capacity, these advanced radios consume 2 to 4 times more power than their 4G counterparts.
And since you have to deploy 4 or 5 times as many of these small cells because of the coverage gap, the energy use just compounds exponentially.
Exactly right. When operators look at the life cycle cost, the soaring energy demands for the radios themselves, plus the massive cooling infrastructure you need to manage the heat at these dense cell sites, it just stifles investment. The critique mentioned this economic severity. Operators are paying significantly more in utility bills just to maintain their 5G footprint,
making it too expensive to keep expanding.
It makes further densification economically prohibitive in a lot of regions. Sustainability and economics are completely linked here.
And finally, let's touch on security and complexity. The move to software-defined networks was sold as a benefit, but it also introduced a whole new set of risks.
Well, the shift to a service-based architecture, the SBA, in 5G, which relies on virtual machines and APIs, it opened up a whole new attack surface.
So flexibility came at a price.
It came at the cost of simplicity, for sure. We now see vulnerability vectors centered around API misuse, which can be exploited to get unauthorized access to core functions. And network slicing.
The idea you can create separate logical networks for different services.
Yeah, one slice for ultra-low latency, one for high bandwidth. It creates huge risks if the isolation between those slices gets compromised.
And the convergence of virtualization, edge computing, massive IoT, it just makes the whole system profoundly complex to manage.
And 5G systems really struggle to manage that complexity on their own. They still need significant human intervention, human troubleshooting, especially when you're integrating multiple virtualized functions. That complexity is just not manageable at the scale 6G is promising without automation baked in from the start.
So to sum up part one, 5G was a brilliant success for basic speeds and foundational IoT, but it failed the test of ubiquity because of physics. It failed the test of autonomy due to systemic latency. And it failed the test of long-term economic viability because of its huge energy appetite.
And that's what justifies the need for a revolutionary blueprint, not just another incremental upgrade. Which brings us right to the core mandate for 6G. The performance metrics required to realize this vision of fully autonomous systems and planetary digital sensing, they force a complete architectural rethink. This is what we're calling the generational leap in metrics.
Okay, let's put these targets into sharp focus for you, the listener. The numbers here are, frankly, astonishing.
They really are. So if 5G gave us, say, 10 to 20 Gbps peak downlink speeds, 6G is targeting 1 terabit per second.
1,000 gigabits per second.
1,000. That's a minimum of a 50-fold increase in throughput. It enables applications like holographic communications that just aren't possible today.
A terabit is a massive conceptual jump. Okay, what about the latency target?
This is the most critical one for the autonomous future. 5G aimed for 1 millisecond, but often landed around 5 meters in reality. 6G targets less than 1 microsecond.
A microsecond.
Yes. That is a 1,000-fold reduction from the 5G ideal, moving decision-making into the realm of near instantaneous physical response.
And the scale of connectivity, the massive machine pillar.
5G achieved 1 million devices per square kilometer. 6G is targeting 10 million or more devices per square kilometer. That density is what's necessary for truly pervasive sensing, where every surface, every piece of infrastructure, every wearable device is connected.
And finally, the essential one, the one to address the operational headache of 5G, energy efficiency.
Where 5G offered maybe a 10x improvement over the 4G baseline, 6G is targeting a 100x improvement over that same 4G baseline.
Wow.
High speed has to be delivered sustainably and affordably. It has to be.
This level of transformation, it doesn't come from just tweaking existing standards. It needs a whole new framework. And the source material defines this through the 5 core pillars of 6G architecture. Let's start with the physical enabler for that massive speed increase. Pillar 1, terahertz radio.
Right. Terahertz refers to the terahertz spectrum. It typically spans from 100 gigahertz up to 1 terahertz.
Just to put that in perspective for everyone.
Well, the 5G you use today might max out in the midband around 6 gigahertz, or maybe in the high band room and wave around 28 or 60 gigahertz. We are talking about signals that vibrate 10 to 100 times faster than that.
And that vast, previously untapped bandwidth is the only way you can physically get to a 1 Tbps peak rate.
It's the only way. The wider the available channel, the more data you can push through it.
Yeah.
But, and it's a big but, as we saw with 5G millimeter wave, the higher the frequency, the shorter the wavelength, and the worse the attenuation and scattering become.
So it's the same problem as 5G, but on steroids.
Exactly. The challenge is immense. We're dealing with ultra-short-range transmission. We need entirely new types of materials, new cooling technologies, just to even harness these frequencies. This requires the architecture itself to overcome the physics, which leads us right into the solutions we'll talk about in part 3.
Okay. Pillar 2 is the brain of the network, the AI native core. Now, 5G had some AI features, the NWDAF, right, the network data analytics function, but this is a foundational redesign.
Oh, it's the critical distinction. It's the difference between intelligence as an add-on and intelligence embedded at birth. In 5G, the NWDAF was an external function. It analyzed data and a recommended action.
But a human still had to do something.
A human or a centralized system still had to act. The 6G AI native core moves to full autonomy.
So how does that autonomous intelligence work conceptually?
It means every microservice within the core network, every single component that manages identity, mobility sessions is designed to be intent-based and self-evolving. The network operates in this continuous sense, predict, act, optimized loop.
Give me an example.
Okay, so instead of waiting for a network failure, the AI predicts heavy XR traffic building up in a specific downtown block at 4 p.m. It knows this based on social patterns, historical data. It then autonomously spins up and allocates compute, spectrum, and user plane resources 10 minutes in advance.
All without human oversight.
Entirely. It completely bypasses human oversight. So it changes the job of the network operator from troubleshooting failed systems to simply defining the quality experience they want to deliver.
The what, not the how.
Precisely. And this is key to achieving that 90% reduction in network failures and managing the insane complexity of a trillion-device network.
Pillar 3 might be the most paradigm-shifting idea here. Integrated sensing and communication, or ISAC. We're collapsing two traditionally separate functions, communication and radar, into one system.
ISAC is the technology that transforms the network radio from just a transmitter of bits into a comprehensive sensory organ for the physical world.
A sensory organ.
Yes. Instead of using separate hardware for radar and separate hardware for data transmission, a single shared radio waveform does both duties simultaneously.
And what kind of sensing are we talking about here?
Everything from simple presence detection to really fine-grained object tracking and highly accurate gesture recognition.
How?
By analyzing the unique signatures of the reflected signal, the ISAC engine can map the environment, the location, the velocity, even the subtle movements of objects, all with centimeter precision.
And that environmental awareness is what's crucial for things like autonomous mobility.
It's crucial for that, for robotics, and for the fidelity you need to build accurate, real-time digital twins of entire cities or factories.
Okay, if ISAC is the sensor, Pillar 4 addresses the coverage problem 5G couldn't solve. Cell-free massive MIMO. We're ending the concept of the cell boundary.
The traditional cellular architecture is based on these discrete cells, which inevitably leads to the cell edge problem.
Right, where your call drops when you're on the border between two towers.
Exactly. Performance degrades, and your device has to execute a difficult and time-consuming handover. Cell-free massive MIMO it eliminates this failure point.
So how does the architecture change physically? What does it look like?
Instead of a few large cell towers, you have thousands of distributed smaller antenna ports. They're not traditional base stations. And they're all connected to a centralized processing unit.
And they all work together.
They operate collaboratively as one unified, extremely large giant cell.
Yeah.
Every single antenna contributes power and resources to serving every single user all at the same time.
Which means
no handovers, period. The user device is always served by the network as a whole. This guarantees a uniform quality of service, regardless of where you are or how you're moving within the coverage area. And it enables massive spectral reuse, which vastly improves efficiency.
And finally, Pillar 5. This one addresses the 100% global coverage mandate, non-terrestrial networks, or NTN.
We established that 5G failed to bridge the rural and ocean coverage gaps because of the physical limits of terrestrial high-frequency spectrum. NTN solves this by building a seamless, multi-tiered network architecture.
Multi-tiered.
Yeah. It includes low Earth orbit satellites, LEOs, like Starlink and others, geostationary Earth orbit, or GEO, satellites, high-altitude platform stations, HPS, which are basically high-flying drones or pseudo-satellites, and unmanned aerial vehicles, UAVs.
And the key word there you used is seamless.
It is. The goal is to integrate these space and aerial segments directly into the 6G core. This ensures that a device's identity, its session continuity, and its quality of service are all maintained whether it's communicating via a ground tower or a LEO satellite flying overhead.
So it eliminates the gaps.
It eliminates the geographical coverage gaps and provides robust, resilient backup communication, which is critical during things like natural disasters.
Okay, so we've established the architectural pillars. Now let's see the practical payoff. How do these revolutionary concepts directly solve the 5G limitations we talked about?
Do it.
First, let's tackle the toughest one, solving indoor coverage with programmable surfaces. If tiered signals are blocked even more easily than ESA wave, how on earth do you ensure deep indoor penetration? The answer is something called reconfigurable intelligent surfaces, or RIS.
This is a breakthrough in electromagnetic manipulation. It really is. RIS are essentially smart panels. You can think of them like wallpaper or building facades. And they're composed of thousands of tiny passive elements called programmable meta-atoms.
Okay, explain the physics of these meta-atoms for me.
Unlike a traditional repeater or a small cell, which uses active RF chains and consumes a lot of power to receive, amplify, and then rebroadcast a signal, RIS is passive.
Passive, meaning no power.
Almost no power. When an incoming TX or milliwave signal hits the RIS panel, the meta-atoms dynamically adjust their phase shifts. Think of them like thousands of tiny programmable mirrors. They don't generate power, they just redirect the existing radio waves.
So if the original signal's line of sight is blocked by a wall, the RAS panel on the outside of the building or on an interior wall, it intercepts that signal and then steers it around the obstacle.
That is the core insight. RIS creates a virtual line-of-sight path, an artificial clear path for the wave, which was physically impossible before.
And that solves the penetration challenge for T-Arts communication.
It does. And this passive nature is a game changer for the 5G energy crisis. RIS consumes nearly zero power, solving the problem of needing to deploy all those energy-hungry active small cells every few hundred meters. It dramatically reduces both CapEx and OpEx for urban densification.
The economic and physical genius of that is hard to overstate. A zero-power solution for a power-hungry problem. Okay, now let's tackle the speed of thought. Breaking the latency barrier to sub-1 microsecond. We know the problem wasn't the radio, but the network delay. So how does 6G achieve that thousand-fold improvement?
It requires integrating three things. You need the short-range T-Hertz links, you need distributed edge AI, and you need the cell-free architecture.
So let's start with the links.
You need T-Hertz short-range links because their inherent wide bandwidth enables faster data transfer, optimized for these ultra-low latency scenarios. But the real structural fix is the computational element, distributed edge AI.
Can you elaborate on the placement of that AI? Where does it live?
In 5G, the critical computational elements, like the brains of network management, were still somewhat centralized. In 6G, the AI inference engines, the actual processing power, are co-located directly with the user plane functions, right at the physical network edge, often within just a few kilometers of the end user device.
So if an autonomous vehicle needs to ask the network a critical question about road conditions ahead, that decision is processed locally. It doesn't have to go to a distant cloud data center.
Exactly. By eliminating that cloud round-trip delay, you instantly save tens of milliseconds. Combine that with the predictive capabilities of the AI native core, which pre-allocates resources and anticipates data needs before the request even arrives. And you move from millisecond decision-making to microsecond responsiveness.
That's what's essential for those time-critical applications.
Essential. It's where 1 microsecond of delay can lead to failure.
Okay, I have to challenge you on this, though. 1 microsecond is incredibly fast. Given the physics constraints, the speed of light, the need for multiple computational steps, is this truly achievable for end-to-end communication, or is it more of an idealized lab metric?
That's a great question. It's definitely an idealized metric, but it is the architectural target. The sources suggest that 6G will achieve this target consistently for very specific, short-range, mission-critical links, where computation is highly localized at the far edge.
So not for my everyday web browsing.
Probably not. But for, say, local vehicle-to-vehicle communications within a controlled factory or a self-driving car cluster. Yes, you can reliably hit sub-microsecond levels because the data never leaves the immediate vicinity. For wider area, general consumer use, the goal is still aggressive ultra-low latency, but that microsecond target is what validates the entire architectural overhaul.
That makes sense. Okay, that brings us back to the green network imperative and achieving that 100x efficiency. The 5G energy crisis was characterized by the high consumption of massive MIMO radios. How does 6G resolve this financial and environmental drain?
It's a robust three-pronged strategy that fundamentally changes how power is used. First, we already talked about the passive nature of RAS reflection. That's basically signal delivery without paying the energy bill for active broadcasting. It's an enormous energy saving right there.
And the second component of the energy fix.
That's AI sleep scheduling. This is driven by the AI native core. Instead of having network components running at high power 247, machine learning algorithms analyze traffic patterns in real time and, more importantly, they predict future demand.
Okay.
Based on this prediction, the AI dynamically deactivates or puts into deep sleep mode specific components within the radio access network, things like individual radio chains or processing units, during anticipated low traffic periods.
So if the AI knows traffic drops 70% between 2 a.m. and 5 a.m., it just shuts down the non-essential parts of the tower to save power.
Precisely. This dynamic activation based on predicted need can cut RAN power consumption by up to 50% without impacting service quality. It directly combats the high consumption of those massive MIMO units. The third solution comes from the physics of T-Hertz itself, highly directional T-Hertz beams.
Now, beamforming isn't new. 5G uses it. How is T-Hertz directional beaming different?
Because the T-Hertz wavelength is so incredibly short, the beamforming required to focus the energy becomes incredibly precise and narrow. Instead of broadcasting radio energy broadly into the environment, which wastes a ton of power.
When no one is listening.
Right. 6G concentrates the energy precisely onto the user device. This highly focused transmission minimizes energy dissipation and maximizes the useful power delivered.
And finally, we have to look ahead. The monumental security challenge that 6G must anticipate, the quantum threat.
The looming inevitability of quantum computing is an existential threat to all of our current internet security. It's that simple.
Explain that threat.
Today's public key cryptography, RSA, and elliptic curve cryptography, it all relies on mathematical problems that a sufficiently powerful quantum computer could solve in minutes. It would break the encryption protecting everything from your banking to military communications.
So 6G must be quantum-proof from day one. What is the defense strategy?
The 6G defense strategy is layered and proactive. First, the mandatory adoption of post-quantum cryptography, or PQC. This involves shifting to mathematical systems that are believed to be resistant to quantum attacks, like lattice-based algorithms and hash-based signatures.
And these have to be integrated everywhere.
Everywhere, into all critical infrastructure, session key exchange, and authentication protocols.
And beyond the math, how does the architecture protect itself?
By embedding a zero-trust architecture system-wide. Meaning instead of perimeter defense, the network assumes no user, no device, no microservice is inherently trustworthy, even if it's internal. You have continuous granular verification of identity and access privileges enforced throughout the entire network fabric.
And that's coupled with blockchain.
Yes, coupled with the use of distributed ledger technology blockchain for tamper-proof device identity verification and provenance tracking.
And the final layer, bringing the AI back in.
Right. AI-based threat prediction. The autonomous core is constantly analyzing network traffic and behavioral patterns across all the segments, terrestrial, aerial, non-terrestrial. The AI neural networks are trained to spot anomalous traffic flows, lateral movements, or unusual resource requests that indicate a developing attack. It moves security from patching vulnerabilities after discovery to predictive prevention before exploitation.
So we have the problems and we have the revolutionary solutions. The big question still remains, though. How do we go from the 5G network we have today to the 6G network that operates on Thertz, ISAC, and RIS? It can't be a sudden switch.
No, it has to be a careful evolution, and it starts with 5G Advanced, or 5GA, acting as the bridge.
5G Advanced.
Yes, it's defined by the 3GPP standards in releases 18 and 19. This period, which is roughly 2024 to 2026, is where the initial concepts of 6G are tested and standardized within the existing 5G framework.
So what 6G features are actually being prototyped in 5GA?
Several foundational elements. Release 18 begins the true standardization of the AI native RAN. It's introducing functions that use machine learning for advanced mobility prediction, optimizing resource allocation, and advanced XR support.
And the satellites.
Crucially, yes. It also starts the full standardization of NTN integration. Operators are essentially integrating space communications and early AI orchestration features into their existing 5G infrastructure. They're preparing the groundwork for the more radical shift to TRs and RIS later on.
Let's talk about the hard dates then, the strategic timeline. Where are we headed globally with this?
We are firmly in the 5GA commercialization phase right now. The source outlines that pre-standard 6G trials. This is where companies and research consortiums like Europe's HexaX, the US NextG Alliance, and the Pirate 6G Alliance begin testing things like passive RIS functionality, and early TRs links are expected between 2026 and 2028.
A pre-standard race.
A highly competitive one, yes. And the standards creation is centralized by the ITU.
The International Telecommunication Union.
Correct. The ITU is scheduled to finalize the technical specifications under the IMT 2030 framework in 2028. Once those global KPIs, the latency, speed, density targets are locked in, the industry moves into mass equipment manufacturing and deployment.
Which leads to
the expected commercial 6G launch, beginning around 2030 and beyond. It's a timeline that requires massive global coordination and investment.
You know, you mentioned the difficulty of the 5G rollout, especially dealing with local politics and the huge capex for densification. Given that 6G requires deploying entirely new spectrum, new hardware like RIS panels, new infrastructure like satellites, isn't that 2030 commercial launch timeline a little overly ambitious?
That is a critical challenge. And the source acknowledges the complexity, particularly around the cost of new equipment and the regulatory hurdles for tiered spectrum allocation, which is still largely unlicensed globally.
So what's the driver then?
It's economic necessity. Because 5G's energy consumption and latency ceiling are so high, enterprises must move to the new autonomous capabilities that 6G offers to maintain a competitive edge. The market demand from Industry 5.0 and the defense sector, that creates the economic gravity needed to force this aggressive timeline.
And the RS panels might actually help.
Exactly. The passive nature of RIS actually simplifies the densification problem, potentially making deployment easier in some ways than the power-hungry active small cells of 5G.
The economic driver is key. This isn't just about faster personal devices, it's an entire economic platform. We're talking about an explosive market potential that is fundamentally an enterprise-first revolution.
The market forecast is truly staggering. It's a projected $1.0 to $1.4 trillion global market by 2035.
$1 trillion.
And the source highlights a major shift. Enterprise services, industrial automation, and specialized governmental applications are expected to command over 70% of that total revenue.
That's a huge departure from 4G and early 5G.
A dramatic one. Consumer subscriptions dominated the financial landscape for those generations. Not anymore.
So what are the killer apps driving this trillion-dollar opportunity? The transformative use cases that really require 1 TVPs and sub-microsecond latency?
Let's start with holographic telepresence. We're not talking about flat video calls anymore.
Right.
This uses the massive bandwidth and low latency to enable true 3D remote presence across continents with real-time visual and spatial fidelity. When you integrate that with haptic feedback, the sense of touch, you revolutionize remote collaboration, education, entertainment. You create a seamless digital identity that can exist anywhere.
Next up, the potential in life-changing services. Extended reality, or XR, healthcare.
This is a perfect demonstration of microsecond latency married to ISA's precision sensing. 6G enables remote surgical procedures where the surgeon can perform micron-level movements with immediate haptic feedback. It removes the risk of time delay errors.
And diagnostics.
Holographic diagnostics and advanced patient monitoring can bridge those critical urban-rural divides, democratizing access to specialized medical expertise through truly immersive, reliable platforms.
And then the autonomous future, autonomous mobility.
Vehicle to everything, or V2X, communication moves way beyond simple collision warnings. With ISAC, the network itself provides cooperative perception.
What does that mean?
The network tells the self-driving truck not just what its own radar sees, but what's happening 2 blocks around the corner. It's sensing pedestrians, unexpected traffic, or infrastructure failures that the truck's onboard sensors could not possibly detect.
Wow.
This real-time, microsecond orchestration of intelligent urban infrastructure enables zero-accident transportation ecosystems. It can manage complex autonomous drone corridors via that end-to-end integration.
And finally, the backbone of future production, Industry 5.0.
This is where the concept of the digital twin becomes fully functional. The 6G sensory fabric blankets the factory floor, enabling micron-level sensing via ISAC. Every asset, every robotic arm, every component has a perfect real-time digital replica.
And the AI uses that twin.
The AI native core then runs predictive maintenance simulations on this twin, anticipating failures and optimizing processes autonomously. The source suggests this could drive productivity gains of 20 to 30% in highly complex manufacturing.
The value is clearly moving from the connection itself to the intelligent services enabled by it. And this forces a complete shift in new revenue models for operators.
The biggest shift is from selling simple data volume to selling intelligence and functionality through programmable network APIs. Operators can monetize the programmability of the network itself. They can offer developers direct access to real-time sensing data from ISAC, sell specific quality of service guarantees like guaranteed sub-2 microsecond latency for 10 minutes, and monetize highly accurate location and presence data.
So they're selling intelligence as a service or sensing as a service, using the network as a computational platform.
Absolutely. Other emerging models include offering digital twin as a platform services and capitalizing on the global reach of Pillar 5 by offering NTN as a service.
Selling satellite capacity like cloud compute.
Exactly. Bundled seamlessly with terrestrial connectivity, they become orchestration partners for enterprise automation, not just pipe providers.
Given that this trillion-dollar market requires radically different technologies, what are the strategic imperatives for pioneers? What skills should the industry be developing right now?
The skill set evolution is non-trivial. Traditional RF engineers need to adapt, and quickly. 6G pioneers must master 3 core areas. First, AML engineering. They need to move beyond simple network analytics to designing complex reinforcement learning and intent-based autonomous systems.
And second,
tiers in advanced RF engineering. They have to manage the extreme propagation challenges of the new spectrum and design the new materials required for antennas and components.
and the third skill, the one that bridges the communication and physical worlds.
That's ISC expertise. This requires mastering the convergence of traditional communication theory with advanced radar signal processing. Engineers need to understand how to maximize the utility of the shared waveform for both data transmission and centimeter-accurate environmental sensing at the same time. Those who can bridge the digital, physical, and sensory worlds will lead the next decade.
And the source material stresses that the time for early involvement is now.
Correct. Early trial participation, whether it's in the lab, in the field, or through pre-commercial pilots using 5G architecture, is essential for building the institutional knowledge required. The early movers in testing RIS and T-ERTS links today will establish a long-term competitive advantage when the commercial standards are locked in around 2028.
So what does this all mean for you, the listener? If we had to distill the core takeaway of this deep dive into 6G, it's this. 6G is not about making your smartphone marginally faster.
Not at all. It's about building an intelligent, self-optimizing planetary sensory fabric. The architectural solutions in 60 THz radio, cell-free massive MIMO, passive RIS reflection, the AI native core, they're all designed not just to transmit data, but to integrate computation, sensing, and near-instantaneous decision-making directly into the network.
The limitations we exposed in 5G, the economic burden of the energy crisis, the systemic floor on latency, and the physical constraints of coverage, they were the necessary constraints that drove this revolutionary design.
Right.
6G is an intentional design philosophy to fix the physics and the economics of connectivity, all in preparation for a fully autonomous, intelligent world.
And if 5G delivered the blueprint for a connected world, 6G delivers the autonomous operating system for a deeply integrated physical and digital civilization. The shift from network as a pipe to network as a computer and sensor is complete.
And this trajectory, as suggested in the strategic roadmap we analyzed, it doesn't stop at 6G. The discussion must naturally lead us to contemplate the ultimate vision of 7G, which is emerging around 2050.
Indeed. The future beyond 6G focuses on hyper-integration, moving toward quantum communication networks, deploying nanosensor swarms, and crucially, bio-integrated human-centric systems.
IO-integrated.
The aim is to move connectivity into the biological realm, blurring the line between the human nervous system and the planetary network.
That is the provocative thought we'll leave you with today, building on the profound architectural shifts we've unpacked. The ultimate technical and ethical frontier is human-machine convergence. If 6G creates a digital twin of our physical environment, how close are we truly to creating a planetary-scale digital twin of us? And what does that integration mean for the future of individual autonomy and our independent human experience?
Something to ponder as the infrastructure around you silently begins to sense, predict, and optimize your world.
Thank you for joining us for the deep dive. We'll see you next time.